Today's lecture is about primes, greatest common factors, and least common multiples. We're going to start out with some definitions and work our way through looking at how to find greatest common factors, how to find least common multiples, some of the relationships between them. But really, this section is all about getting a better understanding of how integers relate to each other. And that's really important because when you teach elementary school, everything or most things, especially at the beginning, are about integers, and understanding how they relate to each other helps build for later understanding in middle school and high school and beyond. So, starting with the definition, this is probably fairly familiar, maybe not phrased exactly this way before, but pretty familiar. A prime number is a whole number p greater than 1 whose factors are 1 and p. Whole numbers, which are not prime, are called composite. Now notice in here that 1 is not a prime number because a prime number is greater than 1, and a composite is greater than or equal to 2. So the number 1 is neither prime nor composite. It's just special all by itself. All right, we're going to use the divisibility test, which we have talked about and worked with and learned some, to determine whether the following numbers are prime, composite, or neither. And if it's a composite, we're going to give a factor. So 234 is divisible by 2, so it has a factor of 2, so that is composite. 1234, also divisible by 2. We know that from that last digit. 2 is a factor. There are other factors, but all we care about is one of them, so it's composite. 1, 2, 3, 4, 5. 5 is the last digit, so 5 is a factor from our divisibility test for 5. So 12,345 is composite. Moving on to 5,021,863. It's not divisible by 2. We can check and see if it's divisible by 3. So that's our next step here. We're going to add all the digits together. When we do that, we get 25. So this is not divisible by 3 or 9. So as we go through these examples, you should definitely pause the recording anywhere that you want to just stop and do this on your own. So we have looked at 2, not divisible by 2. Here we know not divisible by 3 or 9. So 4, if it's not divisible by 2, it's also not divisible by 4. We can skip that. 5, definitely not divisible by 5. Let's see, 8 is our next test. If it's not divisible by 2, it won't be divisible by 8. 9, we've already figured out, it's not divisible by 9. It's not divisible by 10 because the last digit is not a 0. And so that leaves us with 11 as our next test. And for that, we're going to add and subtract the digits in alternating order. So we're going to have 5 minus 0 plus 2 minus 1 plus 8 minus 6 plus 3. We're going to see what we get. And in fact, we do get 11. So 11 is a factor, which means that 5,021,863 is composite because 11 is a factor. 382, that's divisible by 2, so that's composite. Our next number here, 102,302,320, is composite because 10 is clearly a factor with the 0 on the end. 1, as I was saying a minute ago, is neither prime nor composite, so that's neither. And then it turns out 97 is a prime. Okay, next we're going to look at the sieve of Eratosthenes. Even with the pronunciation written there, I get it wrong sometimes. What this is, when we talk about a sieve, you should think of a sifter that you have in your kitchen or with cooking stuff. So it's going to allow smaller things to sift through the holes and leave other things behind. That's the same idea here. What we're going to do is we are going to use a sieve which gets rid of multiples of things, because if we have a number which is a multiple of something else, then that something else is a factor. In other words, that number is composite. So we want to get rid of anything that is a multiple of something smaller. And that's what we're going to do with the sieve of Eratosthenes. And what you should do as we go along is follow along and on your page, mark things out as we go. So what we're going to do here is we're going to look only at the primes between 2 and 108. And we are going to figure out which of these numbers are actually primes. We could do this with many more numbers than this, but you'll see why we're going to stop here just at 108, because we're going to get tired of doing this. Okay, so first of all, what we're going to do is we're going to look at multiples of 2. 2 is a prime number because its only factors are 1 and itself, 2. So it is a prime number. It's not a fabulous prime because, primes really shouldn't be even because, even numbers are usually composite. So anyway, just a little side note there. But we're going to cross out every multiple of 2 that we get in the list. So they're highlighted and crossed out there. So you should go ahead and cross out all of your multiples of 2, all of the evens except 2 on the list. Okay, so that's going to leave behind 2. And then we're going to move to the next number in our list here, which is 3. And we're going to go through and we are going to cross out all of the multiples of 3, which we have not already crossed out. So for example, 6, that is even. It's also a multiple of 3. We've already crossed it out. I didn't cross it out again, but you could keep in mind that, yeah, that is also a multiple of 3. So if you go through your list, we're going to mark off everything that is a multiple of 3 that we haven't already marked off. And so that's taken out a whole bunch of other numbers. And we keep going here. So go ahead and take your time to do that and then move on. We'd already crossed out 4. The next number in the list is 5. So we're looking at 5 here, and we're going to cross out every multiple of 5 that we have not already crossed out. For example, 10, 20, 30, we've already crossed those out previously. Maybe for more than one reason we would have crossed them out. But we're just going to get rid of whatever is left in our group of numbers here up to 108 that is a multiple of 5 that we've not already gotten rid of. All right, then moving to our next not crossed out number, that's going to be 7. So when we get to 7, we're going to go through our list. We do not have very many more of those that have not already been crossed out with something else, which kind of makes sense because 2 times 7 would have been crossed out already, 3 times 7 already, 5 times 7, 4 times 7 because it would be an even number. So there are a bunch of things in here that have already been crossed out, and we can see we actually only have 3 other numbers that we're going to cross out in this next round. And now we're going to move on. Our next number that's not crossed out yet is 11. So we're going to look at multiples of 11 that have not yet been removed. So I could go back just for a second. So that would have been 22, 33, 44, 55, 66, 77, 88, 99. And then the next one would be 110. So that's it. So now if we think about it, what is going to be left in this list? Well, we have crossed out all of the multiples of 11. So anything higher than this, we would have gotten multiples of already. For example, if we think about 13, 2 times 13 is gone, 3 times 13 is gone, 4 times 13 is gone, 5 times 13, 6 times 13, 7 times 13, and so on. And at some point we get outside of 108 anyway. So now everything that has not been crossed out is a prime. So all of the numbers that are now circled on the screen, those are all the prime numbers between 2 and 108. And as I mentioned before, we could extend this to much larger numbers. Like we could extend this up to 1,000 or higher, but we would get really tired of crossing things out and figuring out what's a multiple and what's not. And even though that's fine, that's not hard to do. For example, multiples of 3, we just do skip counting by 3, and we can do that with any of these numbers, but it gets kind of tedious after a while. All right, this brings us to the fundamental theorem of arithmetic. In mathematics, there are literally thousands and thousands of theorems. So if you ever come across a theorem that has a specific name, not just theorem, that means it's important. It's either important to the theory of mathematics that you're studying, or it was a particularly important discovery that led to something new, or it's something that gets used frequently. And if you come across a theorem that not only has a name, but the word fundamental is in the name, that means it's really extremely important. This theorem is the fundamental theorem of arithmetic, and it says that every whole number bigger than 1 can be written as a product of primes, and it can be done in only one way, except for reordering. Because we know multiplication is commutative, which means that we can rearrange the order of factors and get the same thing. So that's what we mean by except for reordering. So the fundamental theorem of arithmetic is really important to mathematicians for understanding how integers really relate to each other. But what we're going to be focused on here is the relationship between numbers and prime factors. All right, and this brings us to our first example. Okay, so first thing we're going to do here is we're going to find the prime factorization of 3240. And there might have been just a little pause in there. I was fixing something on a slide and came back to this, so I apologize if that was the case. To find this factorization, we're just going to work on factoring 3240 any way that we can using our divisibility tests, things we know are, definitely factors. In this case, for example, 10 is definitely a factor. Now, to do this, I'm going to do this in a pencast. So you should pause now and go follow this link. It'll take you to Blackboard where the pencast for this example is posted. And in this case, you're going to see something you might have seen before, where I'm going to use a tree diagram to factor 3240 into its prime factorization. All right, now that we have already done that prime factorization, we see that we could have a lot of one individual prime factor showing up, and that's where the exponential form of a prime factorization is useful. And the exponential form of a prime factorization is when the prime factorization is written as the product of powers of distinct primes listed in ascending order. So for example, 3240, that is 2 to the third times 3 to the fourth times 5. And when we talk about listing this in ascending order, we're talking about the primes. We don't care what the powers are for that, but here we want 2 to come first. Any 2s you have. 3 next, 5 next, then 7 would be the next prime that we would list if it was one of the factors, and so on. So we're going to practice this a little bit more with the exponential form of some other prime factorizations. So we're going to look at the prime factorization for 3600, 2520, 729, and 110,880. And for those, I did those also in a pencast. So you should pause, follow the link, go watch the pencast so that you can fill this in on your handout. Or, try it yourself. This would be the best thing. Try it yourself first, and then watch the pencast and see whether you got the same thing I did. Next, we are ready to talk about factorials. And factorials, you have probably seen this before. It's where we use the exclamation point. So if n is a whole number, n factorial, so right here, this notation, n with the exclamation point, is said n factorial, is the product found by multiplying together all whole numbers starting with 1 and going up to n. So for example, here we have it written out, but for example, 4 factorial would be 1 times 2 times 3 times 4, which gives us 24 if we multiply it all together. Now, a note about factorials, the numbers get really big really fast. And I'm going to show you an example of this. I'm going to use some software, mathematical software called Mathematica, to show you how this works. Okay, so in Mathematica, what I'm going to do is I'm going to just type in factorial. That's the command in Mathematica. And we were just looking at 4 factorial, so that's 24. Now to get 5 factorial, we would have to multiply together 1 times 2 times 3 times 4, so that's 4 factorial already, and then multiply by 5, and we get 120. So you can see already that the numbers are going up pretty quickly, and we see that. In fact, I'm going to make a table of values here so you can see it. In fact, let's take a second here, but just a second here. So we're going to go from 1 to I'll go up to 20. All right, I'm going to display it in a table. Okay, so we see here 1 factorial, that would just be 1, and then 2 factorial is 1 times 2, which is 2. And then to get 3 factorial, we would have to multiply by 3, and then 4, then 5, and 6, and so on as we keep going. So you can see that the numbers get really big. Already at 12 factorial, we're at 479,001,600. So that's a really getting pretty big pretty fast. And then if I scroll down, we can see here at 20 factorial, this is huge, right? This is hundreds, thousands, 100,000s, millions, billions, trillions, quadrillions. So factorials get really, really big. That's only 20 factorial. For example, if we want to see something that is bigger, let's look at 100 factorial. Look at how many numbers there are in that number. I mean, just look at how many digits. It would be hard to count, but fortunately, we have a command on here which will count how many digits are in there, just so to give you an idea how big factorials get, because this is only at 100, which is a fairly small number if you think about it. And that was not what I wanted to do. Sorry about that. Let's try integer. There's the command I was looking for. Integer length. Okay, there we go. So there are 158 digits in 100 factorial. That's it's a huge number. I mean, we see that already. Now let's go even just a little bit bigger, and let's do 1,000 factorial. So we're just going to find out what the length of it is. So there are 2,568 digits in 1,000 factorial. So factorials are really, really big numbers. And just so you can see that number, displayed, 1,000 factorial, here it is. It takes up, so many lines. But again, that's 2,568 digits just in that number. So factorials get really, really big, really fast, as you were just seeing. Okay. So next we're going to do some examples involving factorials. And remember, we are still thinking about primes and divisible and those sorts of things. So we're going to look at whether 10 factorial is divisible by 30. We're going to find the prime factorization of 10 factorial in exponential form. We're going to find the largest n such that 16 factorial is divisible by 10 to the n, and then the largest n so that 18 factorial is divisible by 12 to the n. But the important thing to keep in mind here, as you look at this, it might sound like completely intimidating because there are words we're maybe less familiar with, and factorials are really big and what in the world's going on with those. But remember, divisible by, that really just means, is that thing a factor of the other number? So when we say, is 10 factorial divisible by 30, we really just want to know, is 30 a factor of 10 factorial? When we find prime factorizations, that's actually not going to be so bad because we have already practiced finding prime factorizations of other numbers. Find the largest n such that 16 factorial is divisible by 10 to the n. Okay, so let's break that down for a second. Divisible by 10 to the n. That means that 10 to the n is a factor of 16 factorial. So we're trying to figure out what is the largest power of n that is a factor of 16 factorial. And then the same thing in our last example, we're trying to find the largest power of 12 that is a factor of 18 factorial. And for those examples, I've done them in a pencast. You were probably prepared for that to be my next thing. So you should pause here and go and watch the prime factorization examples here involving the factorials. Okay, now that we've talked about primes, worked with prime factorizations, we are ready to talk about greatest common factor, sometimes called greatest common divisor, of two whole numbers. We're going to spend some time talking about that, and then we're going to look at least common multiples. So the greatest common factor, or greatest common divisor of two whole numbers, a and b, which we write as GCF of a comma b, is the greatest whole number, which is a factor of both a and b. So what you need to keep in mind here, it's so easy for greatest common factor to just get sort of stuck together. said really quickly, might even just abbreviate to GCF, and it sounds like one individual term. But we want to keep in mind that it's made up of those three different words: greatest, common, and factor. So when we're talking about a greatest common factor of two whole numbers A and B, we are looking for factors of A and B. We are looking for common factors. So they're factors that are factors of both A and B. And then greatest, we want the largest common factor. So it's really easy to lose track of that, but when we say GCF or greatest common factor, because it starts to just blend together and sound like one term. But if you keep that in mind, it's helpful for keeping track of what we're trying to do when we find a greatest common factor of two numbers. Okay, we are going to do several examples here, and you can probably already guess there is a pencast for this. But I just wanted to run through here quickly at the beginning. We're going to do two examples where we list the divisors of the two numbers. That is easy enough to do with small numbers, harder to do with larger numbers or numbers that have lots of factors or divisors. Then we're going to use prime factorizations, and you'll see what that allows us to do, the prime factorizations of those numbers. And again, more practice with the prime factorizations there. Some factor trees come in. What that allows us to do is easily find what are the common factors and what is the greatest common factor we would get. And then this last example, we've got two large numbers that are already factored into their prime factorizations. So we don't have to do the prime factorization first, but we're going to use the same approach for finding the greatest common factor. And so now you should pause and go watch the pencast or try it yourself. Or you might watch the first one and then try the next example, see how that goes from there. But you should go and watch those pencasts now and then come back and we will see another approach for greatest common factors. All right, our next approach for finding greatest common factors uses two things. It uses this lemma and the Euclidean algorithm, which we'll get to again in just a second. But this lemma says that if you divide a number, when you do your long division, so if you divide A by B, we get a quotient and a remainder. So we have A equal BQ plus R. Then the greatest common factor of A and B is the same as the greatest common factor of B, the thing we were dividing by, our divisor, and the remainder. Now, the reason this lemma is helpful is it allows us to move from talking about the greatest common factor of two larger numbers to talking about the greatest common factor of two smaller numbers, which from one of those previous examples, you would have seen it's easier when we're dealing with smaller numbers than larger numbers. Now, this brings us to the Euclidean algorithm. And the way we are going to apply the Euclidean algorithm is that we're going to follow this flow chart because it just basically shows us exactly what to do to use that lemma and find the greatest common factor, greatest common divisor here, using the Euclidean algorithm, which means, remember, algorithm is step by step. This flow chart tells us step by step what to do. So we're starting with our positive whole numbers, A and B. We're going to divide the larger number by the smaller one, and then we're going to look and see if the remainder is 0. If the answer is no, we divide the last divisor by the remainder, and we repeat. When we get that division done, we ask the same question. Is the remainder 0? No. We do it again until we get to yes. In that case, the last divisor is the greatest common divisor or greatest common factor of A and B. So in this example, we're going to use the Euclidean algorithm to find the greatest common factor of 4,567,892 and 2,365,748. So those are two large numbers. It is not at all clear what the greatest common factor should be just looking at the numbers. We could try and do prime factorizations of those, but large numbers are not so easy to do prime factorizations. It can take a really long time, which is why we want another approach. So, another pencast, you probably saw that coming again. This pencast, trust me, it takes a little bit of time. You're going to get a little bit tired maybe of going along and doing these examples. Probably needs an extra sheet of paper. I may not have left you enough space on the handout for this one. And it's going to be a lot of long division. Now, I know it's going to seem tedious, but remember that this is another way for us to find the greatest common factor. So it's nice to be comfortable with another method. Also, the prime factorizations of those two 7-digit numbers might be really hard to do. Whereas doing the long division and finding a remainder and a quotient, that's not such a hard thing to do, even if it is kind of tedious. And it's also good practice for the long division part. So pause here, go watch the pencast, and follow along, write things down as you go. All right, this brings us to our last section, which is about the least common multiple. The least common multiple of two non-zero whole numbers a and b, written LCM for least common multiple of a and b, is the least whole number larger than 0, which is a multiple of both a and b. So again, you want to keep in mind the three words least, common, and multiple. What we're looking for here is a multiple of a multiple of b. We want a common multiple, and we want the smallest, the least common multiple. So this is another term, least common multiple, which sort of blends together and sounds like one thing, but remember it's got those three individual words which have meaning for what we're looking for. Okay, examples. We're going to find least common multiples of these pairs of numbers. First one, the least common multiple of 20 and 28. We are going to do by listing common multiples, and then we're going to find the smallest one that comes up first. So we're going to do that there. And then with our other example, we're going to use prime factorizations because you can imagine looking at multiples of 216 and 2046 could take a while and might not work out nicely for us in terms of finding that least one. We might have to go on for a long time to do that and possibly even give up before we get there. So pause here, go watch the pencast of these two examples, and then we will come back and do the last little bit. And finally, we have another way to compute the least common multiple of two numbers, which is this theorem, which says that you can find the least common multiple of a and b if you know the greatest common factor of a and b, and you find the product of a and b. So the least common multiple of a and b is the product of a times b divided by the greatest common factor. So we're going to use this theorem in our last example. We're going to use Euclid's algorithm to find the greatest common factor, and then we're going to use the formula given in the theorem to find the least common multiple. So here's our example. We're going to use Euclid's algorithm again, and you can refer back to the flowchart if you need to find the greatest common factor of 83, 61, and 75. Then we're going to use the formula from the theorem to find the least common multiple of 83, 61, and 75. And so here you should go to the pencast and watch that last example, fill everything in, and then work on the homework and ask me questions where you have them. And I will see you next time.